In this video, we're going to talk about the residue theorem, which is going to be a very important theorem as we do our later videos on computing different types of integrals. So the theorem here is written in purple. Suppose f is analytic on a simply connected domain D, except at a finite number of isolated singularities z sub 1 through z sub n, which all lie in D. So let's just evaluate that so far. So in this picture, I've just drawn everything as we go through the proof, through the theorem. So the first thing is that we have this domain D. I've drawn green, and everything inside there will be the domain. Now we have that f is analytic on this entire domain, except a finite number of points, z sub 1 through z sub n, that are inside this domain. So all these points are here. I've actually started at z naught, just this is an example, but so at z naught, z sub 1, z sub 2, z sub 3, all the way to z sub n, all these points right here you see in these circles, and I'll explain the circles later. F of z is not analytic at those points, but it's analytic everywhere else inside the domain, and that's the key. Now, we let gamma be a piecewise smooth, positively oriented, closed, simple curve in D, which passes through none of these isolated singularities. So we see that this is our gamma, this pink loop on the outside. Notice that it contains many singularities, but it doesn't pass through any, which is the important part. Okay, so as long as we have that, then the line integral, f of z dz around this gamma is equal to 2 pi I, sum of the residues of f z sub k, where z sub k is inside gamma. So we're taking 2 pi I times the sum of all of the residues that lie inside this gamma. So we see that z sub 1, z sub 2, z sub 3, z sub n, these all lie inside gamma. So if we took the residue of f at each of those points and added them up and multiplied by 2 pi I, we would get this integral. Notice that we don't do it for z naught, because even though z naught is a point where f is not analytic, it's not inside our loop. So we don't even worry about it. Don't even worry about it at all. Okay, so you just worry about things that are inside your loop. So now let's go through a brief proof of this theorem. So we start by letting gamma 1 through gamma n be disjoint positively oriented circles centered at z sub 1 through z sub n. So we see that here. We have each of these isolated singularities. Again, z naught doesn't matter, so we don't care about it. And I've drawn a little circle around each one. Now there's a couple things to be weary about these circles. First thing is they're disjoint, which means you should make them so small that they don't intersect each other. So if you see two are intersecting each other, just make both of them smaller, one of them smaller, just so they don't intersect each other. Again, these circles should be also inside this gamma. They shouldn't go outside gamma, so just make them small enough so they're inside gamma. And the big thing is that they're positively oriented. So there might be some ambiguity from previous videos about what positively oriented means. So let me just clear it up. So how it's worded here, these circles are positively oriented. This doesn't say anything about the outside curve gamma or the domain or anything. It just says positively oriented circle. And what does positively oriented mean? It means that you keep the inside of this object on your left. So if we have a circle, if I were just to draw a circle in space and I want it to be positively oriented, I want to keep this inside of the circle right here on my left. So I'm going to travel counterclockwise, okay? So this is why the circle is positively oriented, and that's why all these circles right here are going counterclockwise. We see, even though these might be too small to see, look at this gamma 3. This is pretty big. So the lines I've drawn here, it's going like this, and it's going like this. So it's going counterclockwise, and that's the positively oriented circle. Now you kind of have to distinguish that from if someone comes up to you and says, let the boundary of this, we're going to call this omega, all this space that's inside the gamma, but outside all of these circles. If they tell you that keep the boundary of omega positively oriented, you have to do a different thing. Then you have to do what we've been talking about. You have to make sure that no matter which curve you're traveling on, you're always keeping omega to your left, which means that if you travel around gamma, this is fine, you're going counterclockwise. But if you travel around any of these circles, now you have to switch the orientation. You have to go clockwise, because then by going clockwise, you're keeping omega on your left. But since this statement right here, just this statement in itself doesn't say anything about omega or anything, it just says let the circles themselves be positively oriented, you need to make them counterclockwise. Okay, so just be careful about that notation. Ask your professor if you're not clear on what he means. Okay, so these are all going counterclockwise. So again, omega is the domain with the boundary gamma, gamma 1, gamma 2, and so on all the way to gamma sub n. So it's the curve that we take the inside of gamma and we take away these circles. So we're subtracting all these circles away. Now, the reason we did that is because we want f to be analytic on omega. And is it? Yeah, because f was analytic on the entire domain except at these singularities. And since we took those singularities away by not making them part of the omega anymore, f is analytic on omega. And by Green's theorem and Cauchy's theorem, we know that if we have a closed loop like we do here, and it's analytic on the inside of that closed loop, then we can say the line integral around that closed loop is equal to 0. So we say the line integral around gamma 1 all the way to gamma n is equal to 0. So what else does the line integral equal? It's equal to the sum of the separate line integrals, the sum of the line integral around gamma, plus the one around gamma 1, plus the one around gamma 2, and so on, all the way to gamma n. So let's see that here. So again, that's equal to 0, but it's also equal to the integral around gamma, minus, so this minus, I'll come back to in a second, minus the sum of all these integrals around the little circles. So now, why am I doing this minus? Now I'm doing the minus because we are concerned with the line integral around this omega. We're talking about omega altogether. We're not just talking about one curve at a time. So since we're concerned with omega now, we need to take the line integral around its boundary. And now since we're talking about the boundary of omega, we need to make everything positively oriented. So the integral would be gamma, because it's already positively oriented, minus all of these little circles, because they all need to switch their orientation in this case. So it's going to be the gamma integral minus the sum of all these other integrals, and of course that equals 0 because of Cauchy's theorem. Okay, so what do we learn? We learned that the residue of f at some point in z0 is equal to 1 over 2 pi I integral of f of w dw over some circle that's centered at z0, okay, with radius s. But isn't that just what each of these is? Each of these integrals right here is indeed, so it doesn't have the 2 pi I, but we'll put that in a second. So each of these integrals is the integral of f of w dw, here written as f of z dz, over a circle centered at that singularity with some radius. But again, we said the radius doesn't matter. We said that the integral is independent of the radius. The residue doesn't matter which radius you pick. So that means that if we just multiply this residue here by 2 pi I, so let's say we multiply by 2 pi I, which means that we multiplied by that side, so this side doesn't exist, then each integral is equal to 2 pi I residue of f at that point, which means that if we're adding up all of these integrals, and what we're actually doing is adding up 2 pi I times the sum of all of these residues. So really what we have here is integral of f of z dz around this gamma minus the sum of the 2 pi I times the residues. So I just replaced this integrals, which is the same as 2 pi I times the sum of the residues, okay? And since that's equal to 0, the natural thing to do would be to equate them. So we're going to say the final result, which is the residue theorem, says that the integral of f of z dz around gamma, the biggest outside loop, is equal to the sum of the integrals from k equals 1 to k equals n of 2 pi I sum of the residues f at zk. At z sub k. And just a final note, remember that you only take the residues of isolated singularities inside gamma. So just to note, this z0, even though it is an isolated singularity of f, it's not inside the loop we're currently considering, so we don't need to worry about it. And you're just going to cause more trouble for yourself by worrying about it, because you're going to get the wrong answer, and you're going to end up just doing more work. So it's better just to consider stuff inside gamma, and you kind of want to make gamma as small as possible so you can consider as few isolated singularities as possible. So in the coming videos, we're going to learn lots of different types of integrals, both real and not real integrals, and learn how to integrate them using this residue theorem technique.